Yeah, can you all see the slides? Can you all see the slide?
Not yet, ma'am.
No,
Not
ma'am.
yet?
Now we can.
Now we can see,
Yes,
ma'am.
yes.
Okay. Okay. So yeah. So as I was saying, so so if we summarize, so every aircraft structure has three components: the skin, the longitudinal member, and the transverse member. So we have to keep in mind that different forms of loading come to an is experienced by an aircraft structure. It could be a bending load, it could be a torsional load, it could be a shear load. So you have studied all these loads in your first year mechanics and also in your second course, right? So this different forms of loading, which could be a compressive load, a tensile load, a bending load, a torsional load, and a shear load, produces different form of stresses. It could be normal stress, it could be all possible normal stress, it could be the shear stress. Now you have to understand that the primary component, primary function of these aircraft structures is to withstand this structural load and perform the given function. Now, the job of skin, longitudinal and transverse member is to carry this load and sustain this load while delivering the function. Now, almost all these components, skin, longitudinal and transverse member, more or less carry all forms of load. Transverse, I mean bending, torsion or compressive or shear. But each of this component is primarily associated with a form of loading. Okay, so while I have written all these points, all these bullets corresponding to each structural component, these blue points, the points which are given in blue fonts, are the primary structural function of the respective component. So the primary structural function of skin is to transmit the aerodynamic force to the longitudinal and the transverse supporting member. Okay, so the aerodynamic force first acts on the skin, which forms the aerodynamic surface, and this aerodynamic force is then transmitted to the longitudinal and transverse member. The second primary job of skin is to develop shearing stresses that equilibrate the applied torsional moment and the shear force. Okay, so many of you all might be aware that when there is a torsional load or a shear force, then shearing stresses are produced in the structure. So a primary job of the skin is to develop shearing stress and thereby equilibrate the torsional and the applied torsional and the shear forces. These things will get more clear as we go through the analysis. You will realize why the skin will withstand the torsional load. Okay, and the third important function of skin is to provide the aerodynamic surface and cover for the content of the vehicle. Okay, so all of you all might be knowing that the wing has this fuel tank, the fuel storage and other instrumentation. So the skin also provides a cover along with providing the aerodynamic surface for the wing as well as fuselage. Okay. Apart from these three primary functions of the skin, there are other secondary structural function of the wing, which is to act as longitudinal member in equilibrating the applied bending load. But you should keep in mind that these are not very important. So we should rather not even bother much about discussing this component. Okay, so these three are the primary functions of a wing. Now let us go into the longitudinal member, which could be stringer, which could be spar, which could be a longeron. So the primary function of a longitudinal member is to resist bending mode and axial load. Okay, so if I have a longitudinal member and I give and it experiences a load like this, okay, many of you all know that this load is going to produce a moment, a bending moment. Okay, so the primary job of the longitudinal member is to develop normal stress and thereby equilibrate the bending moment. That is one. And second is that a wing can also experience an axial force like this. Okay, and the other job of this stringer is to resist this axial force by producing some normal stresses. Okay. The second important job of the stringer, stringer or longitudinal elements, as I mentioned earlier, they actually divide the skin into smaller portions. So the skin is actually divided into smaller parts by these stringers and thereby increases the buckling stresses, or as I should say, it prevents buckling of the skin and the large deformation that happens due to the buckling of the string. Okay, and of course, apart from these two primary functions, there is a secondary function, which is that it, along with the skin, I mean, it helps the skin to resist axial and hook stresses. But again, I mean, that's not very important. I mean, these two blue colored bullets are the most important points. Now comes the transverse member, which could be ribs, which could be frames, and which could be bulkhead. Okay. Now, you should keep this in mind that unlike skin and the stringers or the longitudinal member, which participate in developing stresses so as to equilibrate the externally applied force, the transverse member does not perform in a similar way. They have a different set of job. Their primary job is to maintain the cross-sectional shape, okay, of the aerodynamic surfaces and fuselage, and also, that is the first point, they also transmit concentrated load, which is like the weight of a fixture or of an instrumentation, and the thrust that comes from the engine or landing gear to a wing or the fuselage structure. Okay, so they are usually a bulkhead or a frame or a rib is placed in a location where the aircraft is designed to experience a concentrated load, maybe because of the engine thrust, maybe because of the weight of a certain component, instrumentation, okay, certain fixtures and all. Then the third function is to redistribute stresses around structural discontinuity. So you will see if there is a cutout or something in a fuselage or a wing, usually a ring or a bulkhead kind of structure is a rib or a bulkhead kind of structure is actually placed in those regions of cutout. Okay, and of course, they also provide edge resistance for skin panels to increase buckling stresses. This probably you will not be able to appreciate now till we go into the topic of buckling, which will happen at the end of the course. And they also provide end cells for pressurized fuselage. Okay, so this is again not strictly a structural function, but rather a secondary function that this transverse member participating to. Okay, so with this, we are kind of done with the introduction of the aircraft structure. Now I will briefly give an introduction into the material aspect of aircraft structure, just to give you all an exposure of the kind of material that is used for aircraft structure. So at this point, do you have any questions before I move into materials?
Ma'am,
Ma'am, you are muted.
Ma'am, your audio is off.
No audio.
Yeah, can you hear me now?
Yes, ma'am. Ma'am, your audio is off again.
Yeah, can you all hear me now?
Yes, ma'am.
Yeah, can you see the slides?
Yes.
Yes.
Okay, okay. So so where did you all lose me? I mean, you could hear all this that I have.
Yes, ma'am. We were going to start the next slide.
Okay, okay. So any questions at this point?
Ma'am,
Yeah.
can you just explain again what are edge restraints for skin panels?
So see, I mean, there are see, you imagine a Coke can, okay, and if you try to crush the Coke can, okay, using a compressive stress, the crushing, it's a problem of buckling, right? When you take a Coke can and you kind of give a compressive force at the two edges, okay, you can imagine the fuselage is almost like a Coke can. And now if you want to crush the Coke can will not get crushed, but it will rather buckle and get deformed. Now this deformation get restricted when you, because of the two edges of the Coke can. It's difficult to crush the Coke can because you have those two ends of the Coke can. If those ends were not there, it would have been much more easier to kind of crush the Coke can or buckle the Coke can. Okay, that's what the bulkheads do. So the analysis, the mathematical part, the part that comes from the stress analysis will be done only at the end of the course when we will talk about buckling. But probably you will be able to visualize how, so bulkheads are nothing but the two ends of the Coke can, right? The two fixed end of the Coke can. So those two ends actually resist the compression of the Coke can, and that's what bulkheads do. They resist the compression or the buckling of the fuselage, right? Is does that answer your question to a certain extent?
Yes, ma'am. Yes, ma'am.
Yeah. Okay. Okay. So fine. So let me move into materials for aerospace structures. So okay. So let me talk about a brief history of the uh, material that was used for aircraft structure. As you have seen in the last day's lecture, that it all started with wood and linen or cloth wrapped around the wood. Okay, so the wood first was used to make a truss kind of structure, a two-force member truss, and later it was a semi-monocoque kind of structure where layers of wood were glued with each other to produce a monocoque kind of structure. Okay, but there was several issues with the this use of wood for aircraft construction. So somewhere in 1914, there was a major aircraft accident where a legendary university football coach died in that accident, and that actually created a lot of uh, media attention, and US government kind of banned the use of wood for construction of aircraft. Okay, the accident that happened because of the glue that was used to fix the layers of the wood degraded because of moisture. Okay, and that led to this huge catastrophe, and thereby the use of wood was prohibited. That was one reason, and the other reason was that the wooden aircraft, the supply of this high quality wood, which was usually spruce or birch, were being becoming scarce. Okay, that's one thing, and the other thing was that the craftsmanship required to produce those high quality construction was also becoming rare, and that kind of initiated the use of metal for construction of aircraft. So as I said, in 1915 Zankar F-13 was made out of iron and steel. Okay, but though aluminium is the third largest available metals in Earth, but the use of aluminium was restricted till quite some time because of the constraint in manufacturing and processing of aluminium. Okay, though aluminium is widely available, it was very costly to manufacture, extract and manufacture aluminium. Okay, process and manufacture aluminium from the raw aluminium that was available. It was so costly that it is said that Napoleon had a set of aluminium cutlery which he used to flaunt for all those royal guests that he used to get. I mean that was the kind of rarity people experienced with regards to aluminium. But then in 1909, starting from 1909, the processing and manufacturing of aluminium became much more easier, much more cheaper, and thereby we see the huge use of aluminium alloy, basically aluminium alloy for the construction of aircraft. Now, but of course, recently you must be aware that it's not only aluminium, it's a fiber reinforced composite which makes most part of the aircraft. Okay, so of course, I mean, I cannot talk about what is fiber reinforced composite at this point of time. Okay, but it is basically carbon fibers, mostly, sometimes glass fiber. Okay, carbon fiber which are laid up in a polymer or plastic kind of material, which the advantage of fiber, these are called fiber reinforced composite. So polymer which is reinforced by oriented carbon or glass fiber. Okay, the primary advantage of composite is that they are very lightweight. Okay, the strength to weight ratio is very high. They are corrosion resistant, they are fatigue resistant, and it is tailorable. I mean, you can kind of custom make composite as per your requirement. Okay, there is a full-fledged composite course which you will do at the later part of your in 4th year or so. So let's not get into the detail of it. I'm just talking about it just to give you an exposure about what are the present day aircraft construction materials. So this is a Boeing 777 which has 50% of fiber reinforced composite, okay, 20% of aluminium, and then titanium and other components. Okay, there are certain components which cannot be built from aluminium, so they are made out of steel, like the landing gear. Okay, the landing gear cannot be constructed of aluminium because of the high impact that the landing gear experiences. So what are the requirements of, so saying this, I should also mention that there is still a constant research going on in finding out newer and more suitable material for aircraft construction. One among them is titanium. Okay, most of the fighter aircraft these days are trying to explore the use of titanium as an aircraft construction material. Again, the issue with titanium is not the availability. Okay, it's the issue with titanium is the manufacturing process. It's not yet a well-established large bulk manufacturing process for titanium. The manufacturing process that is there currently is very costly, and it is not economically viable to make use of titanium in aircraft. Though titanium has much more improved quality over aluminium, the strength to weight ratio is also very good. The temperature resistance is extremely high. The fatigue resistance is extremely high. But what is holding back from using titanium, at least for the fighter aircraft, is the lack of proper, easy manufacturing process. So why I'm saying this? I'm saying this for y'all to stay open to this idea that there's a constant research going on in finding out more suitable material for aircraft as well as spacecraft. Okay, so you can probably understand that it all started with wood, ended in composite, and still the pursuit is still there. Okay, so that's what I wanted to convey. Okay, now what is the requirement of a metal for airframe? Of course, high stiffness. That's of course there. That's probably there for almost all kind of structure, not necessarily aircraft structure. The primary thing that is pertinent only to aircraft structure is strength to weight ratio. You need a high strength to weight ratio. So in this prospect context, I wish to say that many components of an aircraft actually undergo a huge oscillatory load or vibratory load, like the fuselage, right? The fuselage is compressed and decompressed several times in their lifespan. Okay, when it is flying, it is compressed. When it is not flying, it is decompressed. So this compression and decompression, it leads to an oscillatory, or what should I say?
Ma'am, we lost your audio.
Ma'am, you are on mute.
Yeah, can you hear me now?
Yes, ma'am.
Yeah. Sorry for, I don't know why this is happening, but it's automatically muting itself. Okay, fine. So, yeah. So what the thing that is pertinent to aircraft structure is the strength to weight ratio. Okay, which is probably not that important for a non-aircraft structure. Okay, so as I was saying, as I was saying, the fuselage and other components of an aircraft structure undergo a lot of fluctuating load. So fatigue is an important problem in aircraft structure. And mild steel is has much more better fatigue characteristics than aluminium. But we prefer aluminium over mild steel because of the strength to weight ratio, higher strength to weight ratio. Okay, so next is the high yield strength. Of course, that is also very common with many other applications of structure. Then there is ductility and of course fatigue resistance. Fatigue is an important problem for aircraft. Then there are corrosion resistance and creep resistance. I will talk briefly about what is meant by creep, ductility later. Okay, but these are the main requirements for an airframe. And then there is the other non material properties that are important to find a metal for an airframe is the availability and the cost, and also machinability and producibility. Okay, we would not choose a metal which is not easily machinable or producible. Okay, so just to show that how important fracture and fatigue is in aircraft structure, which is not so in other civil or mechanical structure, is this example. This is a classical example. I don't know whether many of you all have heard about it. This is an Aloha flight 243. It was a Boeing, I forgot which Boeing was this. So this was a Boeing in 1988. So while it was in the full flight, the top portion of the fuselage just torn away in the mid-air. Okay, the reason was that there was a small fatigue crack that was already there in the fuselage, and which grew while it flew, while it was in the mid-air, and the top portion just kind of torn away from the fuselage. Luckily, miraculously, only one flight attendant died in the whole incident, and all other passengers were saved. Okay, but this shows that how dramatic fatigue can be, okay, if not considered properly. Okay, so that is about fatigue. And then there is about fracture toughness. Probably you don't need to get into this much. And this is the kind of load that the aircraft, say the wing, experiences during its entire flight. Okay, so you can see that the load is highly fluctuating, okay, in several parts of the flight, in the several regimes of the flight. Okay, so this fluctuating load, this repeated compression, decompression, the repeated upward bending and downward bending is what is called fatigue loading. Okay, and fatigue resistance varies from metal to metal. So a metal can have high yield strength, okay, high stiffness but low fatigue resistance. Similarly, a metal with much lower yield strength can have very high fatigue resistance. Okay, so depending upon what component of the aircraft that you are designing, you have to choose the material. Like there are two alloys of aluminium. One is Al2024, one is Al5056. Okay, so Al5056 has much more lower yield strength than Al2024, but it is preferred in certain portion of the wing because it has much more higher fatigue resistance as compared to the Al2024. Similarly, the one parameter that quantifies the fatigue resistance is called the endurance limit. Okay, the endurance limit is the number of cycles of load before it fails under a certain stress condition. Okay, so this is called the endurance limit. Okay, and endurance, we don't need to get into the details of endurance limit. This is not per se in your syllabus, but I'm just trying to give you an idea about what one should consider when one deals with the material for aircraft construction. Because I mean, this is the last course on aircraft structure, last basic course on aircraft structure, and probably you should be acquainted with all these aspects of aircraft structural design. Okay, so endurance limit is a parameter by which we quantify the fatigue resistance of a material. The higher the endurance limit, the better the material is in fatigue resistance. So with this, I am done with a quick introduction to the materials for aircraft structure. In this course, we are not going to talk about materials. That's not the part of the course. I mean, this is just an introduction to give a bit of exposure. So, but nonetheless, any one of you have any questions? Am I audible?
Yes, ma'am.
Yes, ma'am.
You're audible.
Yeah. So, am I going too fast? Should I slow down because I'm not being able to see all? I mean, it's a tendency to go fast. So, is the pace okay?
Yes, ma'am.
Okay,
Yes,
fine,
ma'am.
fine. So, let me quickly wrap up the today's class with a small introduction to the kind of loads that aircraft structure experiences. Okay. The first load is the aerodynamic load. Okay. The lift, drag, gust, whatever the aircraft experiences. So aerodynamic load probably constitute the major part of the load experienced by the structure. So we cannot say what is the aerodynamic load coming on. We as a structural guy cannot say what are the aerodynamic load that is coming on an aircraft structure. The aerodynamics people have to provide us with the load that acts on a structure. So once we know the load, not only the magnitude of the load, okay, we also need to know the distribution of the load, how the load is being distributed over the structure. That also becomes important. Okay, so we need to know the magnitude of the load, the distribution of the load, whether it is and the type of load. The type of load as in whether it is a shear load, a shear force, whether it is a moment, whether it is a torsion. Okay, all this needs to be known before you can go ahead and design the structure. Of course, magnitude of the load is very important. You need to know how it is distributed. You also need to know what are the types of load, whether it's a shear force, moment, torsion, whatever. Axial load. Axial load is also very important. It gives rise to buckling. Okay, if it is compressive, right? So this is what we should get from the other members of the design team who should provide us with the kind of loading. Okay. The other type of load that is experienced is the weight or payloads, the ground load that happens because of taxiing and landing, the reaction force from the ground, the power plant load, the engine load primarily, which is the thrust, and the inertial load that is experienced during different maneuvers. Okay. So different forms of maneuvers. So okay, so with this, we come to the end of this introductory lecture. From next class onward, I will move into the real part of the course, which is analyzing the stress analysis of the structure. So before I move on to the next class, that is going to be on Monday, let me just give you a pre-picture of what we are going to do through the entire course. Okay, so let me just tell you. So from structural point of view, a load can be a bending load, a torsional load, an axial load, which could be both tensile as well as compressive. And there could be a shear force. So this, from structural perspective, okay, these are the kinds of load that we probably will need to analyze. These are the kinds of load that can come on an aircraft structure. The source of this load can be anything. The source of this load can be aerodynamics, weight, ground load, whatever. I mean, we will from now on not bother much about this. For us, it is now, from now onward, it is important whether it is a bending load, a torsion, axial or shear force, bending load or bending moment probably.
Excuse me, ma'am.
Yeah.
Ma'am, in the previous slide, that graph was given of variation of stress throughout the journey of the aeroplane, previous to previous, I guess. So is that specific to a type of stress or is it the total stress?
So this is, I mean, see, this is a very, what should I say, a very heuristic kind of thing. This is not a, sorry, this is not a very precise, don't try to extract meaning out. I mean, what I'm trying to say, suppose I take the bending load acting on a particular location of a wing, this is kind of variation that you see in the bending load.
Okay.
And this is not very precise. This is more of a pictorial kind of representation. Okay.
Okay.
Okay, fine. Yeah. So, yeah, any questions?
Yes, ma'am. What are ground loads? You've written taxiing and landing. So,
Yeah,
like what?
yeah. So
Yeah.
it's the, so when it lands, there is an impact reaction that comes from the ground. That's the reaction force of the ground, right? When the plane touches down, okay, with a high momentum, there would be an opposite impact load on the landing gear, right? That's what
Yes,
I'm
ma'am.
talking about. Okay, okay. So, okay, now let me try to get back to this. So, so we, from now onwards, we will be more bothered whether the load that we are analyzing is of which type. Is it bending, torsion, axial, or shear force? Okay, that's going to be the first job, and we will individually learn how to analyze the structure for each of this load. Okay, so there the first module of the lecture will be, first module of the course would be to understand how to analyze a structure under torsional load. Okay, the second module would be how to analyze the structure on bending load. So this is my first part. This is going to be my second part. This is going to be the third part. And this is going to be the fourth part of the course. Okay, right? So, any questions here? Okay. Okay, so now saying this, so let us assume that we know that my structure is experiencing torsional load and I will analyze the structure for the torsional load. Now, what are we going to analyze? We are going to say a torsional moment of 5 kilonewton meter or millimeter is acting on an aircraft component. I know that. Okay. So I have to find out the shear stresses in that component because of this 5 kilonewton meter torsional load. Okay. Now I will find out the shear stress in the component. I will find out how the shear stress is distributed. And I will see that the maximum shear stress that has developed in this component because of my 5 kilonewton millimeter torsional load is within the ultimate shear strength of the material. Okay, we all know the stress strain curve for a given material. If it is aluminium, all of you all know this stress strain curve, right? All of us know the stress strain curve of an aluminium. Okay, we know the ultimate load of an aluminium. So we have to analyze the structure for the torsional load of 5 kilonewton meter. We have to find out the maximum shear stress, and we have to see whether the maximum shear stress is within the allowable shear strength of the material. If it is not within the allowable, it's going to fail, right? And then the structure is, the design is not proper. Then we have to redesign the whole structure. Okay, so that is the primary motivation of the course. Okay, we will learn in the course how to analyze the structure for each of these 4 types of loading. We will find out what is going to be the stress distribution for each type of this loading, and then we will analyze the stress that is developed in the structure. Okay, that is in summary what we are going to do in this whole course. Now, the second point that I want to tell is that we will deal with beams primarily. Why beams? Because you must be aware now that all this, the primary load carrying members are this longitudinal members, which are the stringers, right? Which are like beam-like structure. It's a very slender 1D kind of structure. Okay, so they can be very well approximated as a beam. So beam analysis would be sufficient to analyze the longitudinal member. And the skin is more of a cell-like structure, which we will talk about later, which also we will talk about. I mean, we will also talk about skins like this, how to analyze skins of this form. Okay, of this form, how to analyze this kind of structure. Okay, this is also a beam-like structure, but with a different cross section, with an aerofoil kind of cross section. This is the skin of a wing is also a beam-like structure because the length is much higher compared to the cross section of this. So, and any questions here?
Ma'am, we another class from 11 o'clock.
Yeah, fine. So I'm done. So we'll meet on Monday. Fine. Thank you.
So, ma'am.
Yeah.
Ma'am, will you be sharing these slides with us, like the first one?
I will upload the slides in Moodle today.
Okay.
Okay, fine. Thank you.
Thank you.
Ma'am, but we are not able to go to the Moodle.
Those who are not being able to access Moodle, please send me an email with your IIT KGP email ID.
Okay.
Okay, yeah, fine. Do it today itself. Fine. Thank you.
Thank you, ma'am.
Thank you.